by going 32 divided by 36. Check that out, what you get. 0.8 repeating. I could also try a different set of numbers, like for example, if I didn't like that or I wasn't sure if that was the right one, I could also maybe do the second divided by the first. So I could also do 28 divided by 32 and see what that is. I'm guessing it's 0.8 something. 0.87? 5. So it looks like here, I mean, I'm somewhere around what we found in our calculator. Remember, we just typed it in and we found y, when we did a b to the x, that the a was 36.25 and the b was 0.866. So these numbers are pretty close. This is 0.89 roughly, this is 0.88 roughly. The calculator is telling us that over time, the general idea is that it's going to be 0.866. So remember, the calculator uses all these algorithms to find the best fitting curve or line. So let's use theirs, just because. We know that in a recursive formula, we need to do a couple things. The first thing we need to do is we need to say where we're starting. So U0 from way back when is my very first number that I would get out, which would be a 36. And then if I wanted UN, that's where we take that UN minus 1, and we say what happens to everything that's going on. And based on what we see, we could have used in the red the 0.8 repeating for what's happening to the next numbers. We could have used the 0.875 for what's happened to the next numbers. Or we can trust our calculator to come up with the best number, which in this case is 0.866. And what that means is that for each subsequent number in my second list, which are my dependent values, on average, I'm going to be taking 0.866 times the previous number. Now, will that give you exactly the next number? Nope. But remember, this recursive equation, or any equation, is a prediction of what's going to happen. It's not what actually happened. That's the experiment up in purple. This brown is the prediction. So we do it based on what our calculator said. If you did put 36 here, that's probably the better one to put because we actually know the starting number. But I would have probably also accepted 36.25 because the calculator spit it out. The difference between this and what we usually use, like what the calculator spit out in orange, is that if we're writing something in an explicit formula, which means you're using a y equals, you would have written it this way. Y equals, and I'll use what the calculator gave me, 36.25 parentheses 0.866 parentheses to the x power. In step 3, it says, find the 8th term using this equation. So not what actually came out of my table, but let's go look in the calculator and see what happens. So now I go to my calculator, and in my y equals, what I'm going to do is I'm going to type that in. 36.25 parentheses 0.866 parentheses to the x power. You hit this button for the power, and then the x is right here where the arrow is. And then hit enter. And it says it wants the 8th term, or after, excuse me, I guess I would say it after 8 rolls. So I can go to my table, and I just type in an 8. Now, if you don't have yours set up the way I do, where it's Ask Auto, you could just scroll down to number 8 and look across, and you should see 11.467. So try that right now and see if you can find it after the 8th roll of the dice. So 11.47 was the answer. And I would say instead of the 8th term, I would say 8th roll. And then we actually did step 3 and step 4 together. The explicit equation that they were talking about, where it says this, the nth term, and they want it in explicit, that's this thing right here. So whenever they talk about explicit, they're talking about the y equals equation. That's what explicit means, y equals. Now, kind of the cool thing, because we have these calculators, when you see the phrase half-life, here's what you do. You look at your calculator and you go, okay, I started out with how many? 36. And if I started with 36, I want to end up to get half of that, 18. And my equation was that I'm going to be multiplying by 0.866, and I don't know how long that's going to take me, or how many rolls, in other words. So I say that my 36 times 0.866 to the x power, when I'm done, when I want half of that left over, it should be equal to 18. And what you're going to do is you're going to take and place the 18 in y2. Oh, I didn't want that color. I'm going to put that in y2, and we already have the other stuff in y1. And this is where we do the second trace 5, enter, enter, arrow, enter stuff that we've been doing in here. So let me show you how that works. So my y equals, I already have that equation. I'm going to go with 36 this time, because I said 36 on the screen. If you're using the 0.25, that's fine, don't worry. And in this y2, I'm going to have 18. Make sure that your plots are off, if you haven't already done that. So I'm going to hit enter to shut mine off, because I don't have mine off. And then I'm just going to zoom 6 and see if it works out. Because remember, we always try to start with zoom 6 if we can as a general window. If it doesn't work out, then oh well. Oh man, I don't see anything. That's garbage. See all that thing over here? That's all I see on my graph. That's because my starting value was 36. So I need to be up at least 36 when I start out for the y value. I can see I'm past 10 for the x, so I'm going to adjust my window. So I go into my window to adjust for the stuff that makes sense. So it doesn't really make sense to go with negative numbers, because obviously I didn't see anything off to the negative. So I'm going to start with 0. And I know it's more than 10, but I really don't know how many more. So because I have no idea, I'm just going to go with 50. Maybe that's good, maybe that's not. And when the space between my x minimum and x maximum is a certain amount, I like to have 10 marks on my graph to see things. So I'm going to go up by 5s. You don't have to go up by 5s, you can go up by 1s, but everything kind of looks squished when you do that. So I like to go up by 10%. And then my y values, I didn't see anything in the negatives, it was all positives. And I know that my starting value was 36, so I'm just going to go up to 40. And then because I went between 0 and 40, I'm going to go up by 4, because that's 10% of 40. And then I'm going to graph it and take a look. And when I graph it and take a look, this curve that's going downward is my exponential decay. I know it's decaying or going down because the number inside the parentheses was less than 1. And then I can see my starting value off to the left, and oh look, I see the line crossing. And what I'm looking for is, when does that occur? So to find that on your calculator, it's really easy and convenient. You can go second, and then trace. That's weird. Second,
trace, there we go, 5, because I want to find out where they intersect. Enter, enter, enter. So I'm going to guess somewhere to the left here, and hit enter, and it tells me that they're intersecting at 4.82. So I write that down, 4.82.
Now, this is talking about how many rolls on the dice it would take for this stuff to happen based on our stuff that we were talking about on page 238, which we didn't actually open our books and look at. But that means about 5 rolls of the dice is when you would expect to be half of the people standing. So, for example, if I started asking questions in class and that question was answered and a certain number of people sat down every time I rolled the dice, the time that there would be 18 people left standing would be roughly about the 5th roll. That's what it's saying. So an example